So the topic of this particular calculus connections video is dealing with rotation. So there's a few different things with rotation that you should be familiar with, angular velocity and angular acceleration. And you should understand these as the analogs to linear velocity and linear acceleration, that we're doing the same kind of thing just in a rotational context. And so angular velocity you've talked about as your omega, but in that calculus world, we can write it as d theta dt, which is just the change in our angle over time, which is exactly what angular velocity is. But this is what it looks like written as a derivative. And then acceleration would just be the second derivative of that change in angle, or the first derivative of that angular velocity. So there's our derivative side of it. On the other side, if we integrate our angular velocity, we get that angular displacement, which instead of how far have you gone forward in a linear context, it's how far have you rotated, which would typically be given in radians. And then if you integrate the angular acceleration, we get that change in velocity from that. So again, topics that you've talked about in your physics classes, in your calculus classes, but this is what they look like together. And so there's several different types of questions that can arise with these kinds of formulas. So you can read this one here. We have 5 graphs, angular velocity as a function of time. And for this one, we just want to be able to identify which one has the greatest angular displacement. So if you need to, pause the video, see if you can figure it out, then start it back up. So with this one, when we're looking for angular displacement, we're looking for, from an angular velocity graph, we're just looking for the area under that curve. We're looking for an integral. So whichever one of these curves has the greatest area under that curve, that greatest integral, is going to have the greatest angular displacement, and that happens with B. So what if we change the wording of this? So in this one, when we're looking at the average angular velocity to get the smallest, remember, average angular velocity would be finding that total integral, which would be that total area, and then dividing it by the change in time. And so to minimize this, to make it the smallest angular velocity, we want that area to be as small as possible, which will happen for A, simply because we have a combination of positive area and a negative area that will cancel each other out and give us 0. So if we think about that angular velocity, we're going forward in time for this first part here, and forward around the circle. But then as time continues on, we're actually changing the direction of that velocity, and now we're going backward around the circle. And so that negative velocity will cancel out that positive velocity and make A the smallest. So then we can actually start getting into equations for these functions. So here we have an angular velocity on a disk given in radians, I guess radians per second, by the equation omega of t equals 9 plus 3t. And now we want angular displacement. So using the function, see if you can find the angular displacement from t equals 0 to 1. So if we have the angular velocity equation and we want angular displacement, that is just integrating to go from velocity to position kind of thing. And so we have the integral of 9 plus 3t dt from 0 to 1. So at this point, you just need to be able to know to do your basic integrals. In this case, with that power, we'll evaluate it from 0 to 1, and we get 10.5 radians for that angular change. Now we can take this up a level. Now we're dealing with a bicycle that has a radius for the wheel of 0.5 meters as it relates to the angular velocity of 2 plus 4t squared. So now we want to know how far the bike travels from 2 to 3. So think about the steps involved in this. See if you can set up the problem here and get the right answer.
We'll try.
Set up the integral the same kind of way here. But now we're integrating from 2 to 3. So this will give us our angular displacement. But we want our actual distance of moving, not just the angular change on the wheel itself. And so do the integral, we get 27.3 radians. That's the angular change on the wheel. So with about 6 radians in each revolution, that would be a little over 3 revolutions of the wheel. But we want to know the actual distance. So we can take our distance equals r theta. You might have it as a different variable for d. You might have s for x. But the distance equals r theta. So 0.5 times that 27 1/3 is approximately 14 meters. So one of the other topics that we can get into with rotation is rotational kinetic energy. Now this will be less about doing a bunch of problems with rotational kinetic energy and more about using it to justify another formula that we will talk more about. So if we have a rotating rigid body, we can't calculate that kinetic energy directly with the 1/2 mv squared because different parts of the mass are different distances from that axis of rotation. That we can't assume that something's just spinning at a point and all the mass is concentrated at one spot. Or that it's just at the outside edge of a ring and somehow that whole mass is out in one radius. And so instead, we have to think of this kinetic energy as an integral through all those different radii from the center of that circle all the way out to the edge. And so we can write the kinetic energy as the integral of 1/2 v squared dm. So this dm is that differential of that mass as we expand outward. But we're still taking a 1/2 mv squared. But it's just integrating from the center out to the edge. But using a couple conversion formulas that we have for rotation, we know that our velocity is equal to r omega, which is the radius times the angular velocity, which we could just separate out into r squared and omega squared. And then the 1/2 omega squared is just a constant. And so we can throw that out in front, assuming we have a constant angular velocity. And then we're left with the integral of r squared dm. So this gives us kinetic energy. But think about the formula for kinetic energy is normally 1/2 mv squared. Well, now our omega has sort of taken the role of that velocity in a rotational context, which means, and the 1/2 is already there, which means this integral of r squared dm is taking the role of the mass. So the integral of r squared dm is, for all intents and purposes, our mass in a rotational system. And this is called our rotational inertia, also known as the moment of inertia, but it's the angular analog for mass. And the idea with this rotational inertia is that the mass acts differently the further it is from the axis of rotation. That the farther out that mass is from the center, the harder it will be to change that rotational velocity. And so it's like the further away the mass is, the more massive it feels, the more impact it has. Whereas if mass is really close to the center, it doesn't have that same kind of massive power. So this is the formula that a lot of these calc-based questions try and take. And so it's not always about calculating this integral, it's more about understanding that this integral is the mass conversion, the mass analog in these rotational systems. So here's an example of one that's just really straightforward of do you understand what this formula is asking about. The moment of inertia, integral of r squared dm is the rotational analog of which one? That's right, it's D, the mass. Some questions will start to go a little bit deeper into what it would mean contextually in a system. So here we have a list of 5 objects, all of the same mass, the same length, but we want to know which one has the greatest rotational inertia about its midpoint. So we have one that's a very light rod with heavy blocks on the end. And so the midpoint of that is going to be the axis of rotation. Or we have a rod that's just uniform, so same mass as the one with the big blocks, but it's uniformly distributed along that rod. Or a non-uniform rod where it starts with a small density at one end, a large density at the other end, and the rotation's still in the very middle. Or do we increase density from the middle out toward the ends? Or do we put the heavy blocks near the midpoint? So if we want to have the greatest rotational inertia about that midpoint, I drew a picture for you there so you can see which midpoint I was talking about, just in case there was any clarification needed. We want that mass to have the greatest inertia, rotational inertia. The mass needs to be as far away from the center as possible. And so concentrating it in those two blocks on either end is going to give us that greatest rotational inertia. D would be pretty high as well, where the density was increasing from the middle out to the ends, but some of that mass is still being concentrated too close to the middle. Whereas for A, all of that mass is shoved to the outside, and that's what we're looking for to get that greatest rotational inertia. So you might find some of these kind of things in the free response questions as well, where you need to start putting together some of these formulas and ideas in a little more complete way. So here we have a person of mass m flying to the left, literally flying, okay, I don't know if they're flying, at a speed of v naught, when she manages to grab onto the rim of a cylinder, a solid cylinder of radius r, length L, mass m, and uniform mass density that rotates without friction about its axis. So using integration, we want to calculate the rotational inertia of the cylinder. So this is a situation where we are going to do some calculation with that integral. But it takes a lot of setup to actually get to the point where we can take an integral. So here's the cylinder that is being grabbed onto. So this person is running, they grab that cylinder, presumably somewhere near the bottom here, and then rotate, woohoo, up to the top, and then spin around and have a lot of fun. So we want the rotational inertia of that cylinder. And so we can start with our integral for rotational inertia, the integral of r squared dm. Now integrating with respect to mass doesn't really make a whole lot of sense. And so we want to convert this into values that do make sense for us. So one thing to remember is that the mass equals the density times the volume. So we know that this has a uniform density throughout it, so that density will be constant. But we have the m equals that density times that volume. So if we take the derivative of this with respect to v, we get dm equals the density times dv. Or if you prefer, you could see it as dm dv equals the density, and then multiply that dv to the other side. So I just took the derivative of that with respect to v. And then the volume, since now we have a derivative with respect to volume, the volume of the cylinder is pi r squared L. So if we take the derivative of this with respect to r, we get dv dr equals 2 pi r L, multiply that dr to the other side, so dv equals 2 pi r L dr. Isn't that wonderful? So now that we know what dv is in terms of all these other variables that we're dealing with, we can plug that back in for dm. So this differential dm that we're dealing with in here, what we just found is that we can write that as the density, which is the mass of our cylinder divided by the volume of the cylinder, pi r squared, big R squared, times L. So that's our density. and then multiply that by what we found for dv, which is 2 pi RL dr. So this can simplify quite a bit into, what do we have, 2m r dr over r squared. So I cancel it out a pi on the top and bottom and an L on the top and bottom. So now this is our dm. So we can plug it into our integral now, the integral of r squared times 2mr over big R squared dr. And now you'll notice that we have an integral that is just in terms of that radius r. So it's a lot going on, a lot of different variables getting thrown around here, but the reason that I wanted to get to r somehow was because the integral of r squared dm has an r in it. That I want my differential at the end to match the r squared that's inside there. And so that's where all these other conversions came from to get that. So this would be the integral of, we can bring a lot of this out in front as constants, the 2m over r squared, and then the little r cubed dr is what we are left with. So now we can actually go and do the integral. We are integrating from 0 to big R. So that is from the center of our cylinder out to the outside edge. And so this gives us 2m over big R squared times little r to the 4th over 4 from r equals 0 to r. And so plugging that in, 2m big R to the 4th over 4 big R squared. We have a few things we can simplify here to get mr squared over 2. There are a couple other analogs here that I want to mention the formulas for. I think we have one more problem here that we can actually do, but just being familiar with the idea here. So torque, this is your rotational analog for force. So where force, you have mass times acceleration. The rotational version of that is torque equals that moment of inertia times the angular acceleration. So it would be like your angular force equals your rotational mass times your rotational acceleration. Same kind of formula and used very similarly. And this brings us into the rotational work. And the work was in one of the other videos. So we talked about that work being your force times your distance. In the calculus side of things, your work at an infinitesimal level is your force times your infinitesimal distance. I think I said that. And we can convert that into the perpendicular force times r d theta. So your r d theta is your change in r at a set r distance. Which we can define as the torque d theta. So if you want the total work done in a rotational setting, normally our work is the integral of f of x dx. Now we can write it as our work being the integral of tau d theta. Is it tau? Torque d theta. I think it is a tau.
I don't think it's tau.
Definitely. That's what I typed in to make this equation.
It's curly T. Is that torque symbol?
So, integrate your torque with respect to theta, and that is essentially a force times the distance. It's just a rotational force that's dependent on how far you are from the axis of rotation, times the angular distance that you rotate that force. Same kind of formula, now just in a rotational context. Using plain words, that's our angular work, equals a rotational force times an angular distance. So that can bring us into questions like this, where the angular position of a wheel is given by an equation theta of t. So that's our angular position at a given time. Measured in radians, time in seconds. And we want to know when the torque on the wheel is equal to 0. So I know there'll be no torque. So we just start with our formula that the torque is the rotational inertia times the angular acceleration. The rotational inertia should be constant. And so the only way for your torque to be 0 is for your angular acceleration to be 0. Well, if we have an angular position, we need to take the derivative to get an angular velocity, and then take its derivative to get an angular acceleration. And if we can find where that equals 0, now we know when the torque is going to equal 0 as well. So we can use a second derivative. So take a minute here, see if you can find that second derivative to get our angular acceleration formula, set it equal to 0, and then use that to find when the torque will be 0. So to get our angular velocity, take the derivative, we get 6t squared minus 12t. To get our angular acceleration, take its derivative, 12t minus 12. And we want to know when that equals 0. And that occurs when t equals 1. Now there is one more thing that might pop up, and it's the idea of rotational power. So you know power is your work over time. In a calculus world, on an infinitesimal level, it is that differential power of work over differential of time. But we just said earlier that work is equal to your torque d theta. So we could rewrite power as torque times d theta dt, and you should recognize d theta dt as your angular velocity. So your power, your angular power, is your angular force times your angular velocity. So again, just another formula that comes into play where we have a linear version of it, and now we also have a rotational version of it in terms of what it looks like in that rotational setting.